like to just start with, because people on the same page of what I view AI is. It's a science of the study of computational mechanisms underlying thought and intelligent behavior. Now, the founders of the field, in their proposal in 1955 for a summer study, said, we're trying to find out how to make machines solve the kinds of problems now reserved for humans. And they defined in their proposal 4 pillars: perception, learning, reasoning, and natural language. And over the last 65, 70 years, a whole variety of fields have come to the fore, and with their own workshops and communities. So it's a pretty broad field these days in terms of all the folks pursuing insights about machine intelligence. And then I want to just address this issue about the perceptions versus reality of advances in AI. The public often hears about Watson and Jeopardy and the IBM system, or self-driving cars, or AlphaGo. But in reality, there's been a stream of innovations that's continually been shared over decades. For example, in the late 90s, working with academics, the US Postal Service put into place, now in place as we speak here, an automatic handwriting recognition system that's zooming through billions of letters per year with a whole analytical pipeline. Now, that said, we are at an inflection point over the last, I'd say, 9 to 12 years, largely around the rise of new kinds of machine learning. It's actually machine learning methods that have been around since the early 90s. We discovered, though, in 2009, that these methods that weren't even as good as some of the other machine learning methods, the traditional ones, these neural net methods, deep neural nets, were simply all this time famished for data. And we didn't have data to feed these systems. And when we started feeding them, originally at Microsoft Research in the summer with Jeff Hinton, looking at speech recognition systems, we discovered that we could actually make speech recognition that actually worked. It was less frustrating. And you can see here that over time, we've actually come down, at least with one data set, to human level and beyond, with the ability to transcribe what's called the switchboard data set. Same methods, very similar, were applied to object recognition. Just about 2 years ago, we showed that we could do better than humans on one of the ImageNet challenges. And then we have new kinds of challenges coming to the fore. I put reading challenge in quotes because people might misinterpret this as actually systems that might actually understand the content of text. But there's a reading challenge done at Stanford, which basically has a computer read Wikipedia articles and then answer questions. And there was kind of a human level reached in that challenge as well by groups at Microsoft Research, my team, my broader team, and also I think it was Alibaba at the time. And besides these wedges of intelligence, we've also had this idea of stringing together and building pipelines, for example, that bring natural language together with vision. And if you showed me as a grad student in the 80s our ability to do this, I would be very impressed that we've gotten this far so quickly, which is automatically captioning imagery. So you see here in black is the machine automatic caption looking at this image, and the human, which human types in, has a typo there. But it's pretty impressive how well these systems are doing these days, and we have to keep on raising the bar and trying new challenges out when it comes to some of these, I would say, narrow tests of intelligence. And research continues now. So we have a bunch of work now going on around the world in video, interpreting activities from video, recognizing complex patterns of behavior over time. And it's really kind of nice to see that companies, the various companies, consumer-oriented companies, enterprise-oriented companies, pressing these advances into new kinds of services like Skype Translator. I mean, just 4 years ago in Tianjin, Rick Rashid, our director of research at the time, was in front of a large audience, and I was with him with a team that had barely gotten speech-to-speech translation working in front of an audience. And he began talking in front of this massive Chinese audience of graduate students. and nothing happened. And we figured, okay, well, we were at the near edge of even trying this. And then it kicked in, and I watched people take English to Mandarin in his own voice. And I watched a young Chinese grad student pull out her headpiece and with tears in her eyes as she heard him speaking in Chinese as he spoke in English in direct translation. And the fact that we were at the edge of our seats 4.5, 5 years ago, and now it's like Skype Translator, many languages, language-to-language translation is amazing to me. In other capabilities, we're seeing the ability to take machine learning to large corporate and to pull out, for example, of email, the promises I make to others. And this is a combination of work in machine learning and social psychology that gives me this service that I depend on now that reminds me of the promises that I've made to others in email as part of Cortana. And I've come to depend on the system because I'm one of these people that makes many promises to others. And then on Thursday, they say, where are those PowerPoint slides? You said by Thursday. And I said, oops. Now Cortana is helping me with the promises, managing the promises here. How many people have seen this before? Where's that title in abstract? It really helps me out. And then there are now services available that people can program to in an attempt to democratize, as the quotes people use, to democratize AI development. So you can sort of build systems that could actually detect faces and ages and genders and emotions and sort of weave these in from the cloud or local edge solutions into your applications. And then just for this group to reflect a little bit, I've been impressed, although it's been slow, with both the deep relationships between psychology in many different forms, not just cognitive, and the pursuits of machine intelligence over the decades. Recently, we're seeing, I would say, an attempt to unify where we look at computational intelligence as being important to understand humans and machines, and maybe moving from the phrase artificial intelligence to computational intelligence is a better concept. But for example, understanding that there could be the same findings showing that models that came from AI are helping us better understand human behavior and abilities, with work by Josh Tenenbaum and Sam Gershman, or Richard Lewis, on taking this idea of bounded optimality, which came out of AI, to now understand how people do visual search and to explain results that have been mysterious over the years. So there are many opportunities at this juncture, both ways, and they span clinical and social and cognitive psychology. And the one I'm going to sort of focus on today, as I dive in, I think you'll be hearing from other people as well, and Cynthia last night, Justine this afternoon, is opportunities in the realm of human-AI collaboration. Sort of machines working with people in a more fluent and fluid way. And I wanted to go back to a long-term dream and pause here for a bit to give us a sense for thinking over the decades on humans and machines working together. So J.C.R. Licklider, who was referred to as Lick, was a program manager at DARPA for many years. And he actually was exposed to this system called Whirlwind in the late 50s, which was built for defense applications. But it was the first system, and it's notable in that it provided feedback at interactive rates, as opposed to the shoe boxes full of cards and so on, and batch processing. And Licklider was reflecting, looking at the Whirlwind system, and he said, wow, I realize this is for defense, but I can imagine that someday people will set the goals, formulate the hypotheses, determine the criteria, and perform evaluations, but the machines will prepare the way for the insights and the decisions in technical and scientific thinking. And this idea of what he called human-computer symbiosis, a colleague whose competence supplements your own. And calling out this will require much tighter coupling between humans and machines. So as a frame of that work, funding programs kicked off. At SRI, Licklider funded a program with Doug Engelbart that gave us this crazy contraption. This is the first mouse. I like the wood veneer there with structure. But the idea was, can humans basically talk to these computers in an interactive way with more of a high bandwidth set of connections, for example. Now, for me, personally in this space, I'll just share a little bit of background on how I first dove into this. I was finishing up my grad school work at Stanford, and I had a special project through some relationships with our department that led me to Mission Control Center in Houston. And I was very impressed to meet the people there, and the people in the lower section there in the front row called the prop section, propulsion section. These people sit and look at the controls when a space shuttle launches or re-enters or is orbiting, and they have to make time-critical decisions of the form, if I abort the mission now at 40 seconds, the shuttle can return to Kennedy Space Center. If I wait, 90 seconds, it goes to Mojave Desert, and a minute, 20 seconds, it lands in Madagascar, and they have these kind of like, just watch the shuttle, they watch all these sensors as they think about this time-critical decision with high stakes. And in doing this work, watching people during launches, so I get to see a nighttime launch, my first goal was, and this was the mission for the proposal, build a Bayesian diagnostic system that understands how the engines work, the propulsion system works. And this was a graphical model that could do a great job of taking in sensor values, hundreds of sensors streaming data to a model that would then give us a probability distribution over faults or possible failures. But you needed to take action, so we actually built a system that would, this is a representation called an influence diagram, which is an action representation, showing that you have to make a decision at some time t, and how long you delay influences duration of process, and based on the system state inferred from that larger model, tells you what the outcome will be, and it's going to advise humans on as to what to do. But we realized, and this is someone I actually worked with down at Mission Control Center, that the goal was actually to inform human beings, not to sort of automatically abort a mission. These were the people responsible, and we had a kind of a narrow system that was reasoning about a particular wedge of a problem. And so we went back to the drawing board with the same models we had built, and we said, something, it's not about the action you should be taking, it's really about expanding open the model to say, what should we display to the human being? It's a different decision problem built on the original model. And to do that well, we had to understand what were the beliefs of the human being at any moment, given the observations. And this led to a system that, instead of giving recommendations necessarily, highlighted on a screen with brighter or less bright, highlighting what information would be most valuable to that operator, the propulsion section operator engineer at this moment. It's a very different solution now that uses a model of belief, dynamically computed. And to give you a sense of what's going on here, this led to a general schematic for how do we build systems to help people, to augment people's abilities that would do joint modeling of beliefs of a human and the world state. So we build a model that actually is a formal model that makes inferences about what someone believes. We have another model which is doing its best to take all the sensor readings from, let's say, a system like the shuttle and reasons about what it thinks are going on given data coming in. So we ended up with two distributions here. And the idea is to take the distribution over human beliefs that we infer, we estimate, and the system predictions, and together compute ideal actions. So that's what we ended up doing in a real system that was working to augment a human's abilities. But moving forward, what are some key challenges in building these systems that someday that JCR Licklider would be really happy and excited about someday? Well, we have to infer human goals in any setting, if a computer is helping a human being. We have to sort of understand a model of complementarity. How can a computer ideally complement a human decision maker or an artist, or someone working with other people, for example? How do we coordinate initiative? And then how do we ground and introduce a level of fluidity with shared understandings on a task? So these are areas of research at Microsoft and other places. I thought I'd march through a few examples of these areas of work and talk a little bit about the relevance to this community as well, where you can all help, and many of you could help, given your special knowledge of human psychology. Well, the dream sequence, we'll call it a dream sequence I'd like to use, is that if we take this blue blob as human cognition, all of our abilities on the y-axis going up, what psychologists have shown us over the last 125 years, ever since Zigernik and others, is that human beings have systematic blind spots, biases, and gaps. And if the question is, could we build computing systems that not just helped in a coarse way, but that understood the nooks and crannies? So here's the dream sequence here. Got to get closer to the control, I guess, to get things to work here, where machine intellect is now going to extend our abilities, specifically along different dimensions. And what's very exciting to people in computer science working in this field is we get to read literature from psychology, the memory literature, the attention literature, the judgment literature, and then do our own studies informed by that to understand in the detailed context of a solution how best to deliver complementary systems to human beings. So the work on our team, we grabbed a few examples spanning attention, memory, and judgment, includes, for example, work over a number of years stemming from around 1999 to 2008 or so on what's the cost of interrupting somebody doing task A with an alert B or another task. What's the cost? And building a component that could be used in many prototypes where you wanted to do multitasking, to understand at any moment the task of shifting, disruption and recovery, for example. Using machine learning from lots of data from human beings and users to build a model of memorability. What's most memorable? What will be a landmark over time? I remember on this project called Life Browser, I'll show shortly, actually running here, we use these models to build a timeline of most memorable moments across all your activities and pictures and meetings with a slider, a volume control, based on these models of memory. This is a Bayesian model of memorability here. But I remember talking to Gordon Bauer about, point me at the literature. What distinctions are the most important distinctions the system should have? And we added a whole bunch of new distinctions that really boosted the power of this model over time. It applies to videos and images and so on. Over here on models of surprise, we actually implemented a model that would predict in traffic, for example, when a human being would be surprised by a machine inference about what traffic would be on a commute home in 30 minutes when there was no surprise now in traffic. So if you believe the surprise model, you shouldn't look at your device unless it thought you'd be surprised, at which time it would alert you, as an example. These are all very important areas. So in this idea of models of complementarity, let me talk a little bit about where things are. So in relatively simplistic combinations of human expertise and machines, we see boosts. So there was a challenge called the Chameleon Grand Challenge in 2016, where a large data set of negatives and positives were put out for competitors. Build a machine learning system that can detect metastatic breast cancer in these lymph node histological sections of lymph node tissue. And it turned out that the human pathologists were indeed, I guess it's good news maybe, superior to the best machine algorithm. However, they made mistakes, 3.4% error, both false positive, false negative. But when you, in a simple way, combined the AI system with the human, you had an 85% reduction in errors when they were jointly used. And my comment was, looking at the work, it was a relatively simplistic combination. So the question is, what might you do in more detail if you actually understood the actual detailed borders? And in a project with Ajay Kumar at Microsoft Research, Severin Hacker, who was an intern from CMU at the time, called CrowdSynth, we looked at this idea of machine perception and human perception, both applied to a task of a citizen science task of looking at pictures of galaxies as generalists, as the general public, and trying to learn how to figure out how to label them and help astronomers with labeling these astronomical, or these pictures of heavenly bodies, thousands of galaxies. Well, it turned out that the solution involved looking at a large data set and building a model that understood how to weave the features seen by a vision system with patterns of voting, with background on each person working, so it's tailored to all the individuals available at the moment, that could predict at any moment the correct answer as well as what the next person would say based on a large number of observations. And we showed that when you did this very, very detailed weave of human perception and machine vision, you could basically get full accuracy of the system with half the human effort, and 95% accuracy with a quarter of human effort. So figuring out how to, what's the cost benefit on the actual detailed complementarity. Now, one area that I'm very interested in that working in right now with a student, but it's part of a larger project over the years, is how do we apply these methods to address some very, very big problems? So about 4 years ago, the British Medical Journal, and there's been several papers like this, but came out and confirmed that yes, avoidable errors in hospitals, typically cognitive errors, are the third most common cause of death all up in the US, right after heart disease and cancer. And these are pretty credible statistics. So the question is, in such a safety critical area, could AI systems that understood human cognition provide like these, this is the image I had in my mind and I finally found one that matched it, these safety nets under the bridge workers. Once in a while they'll fall, and you want to catch them and say, okay, I got you. And here's an example of a model we built several years ago. This is with postdocs Mohsen Bayati and Mark Braverman and ER physician Justin Gatewood at MedStar Hospital in Washington, D.C., not probably far from where we are. Now, the MedStar Washington Hospital Center is in the top 10 urban hospitals in the nation, had a massive data set that we could use over 15 years collected on patient symptoms and so on. And we looked at the emergency room data set, and here's the kind of model we wanted to build. Find patients who are discharged from the ER, see you later, and then within 48 hours, show up at the hospital with a severe problem and are admitted as an inpatient, and with a primary diagnosis upon intake as an inpatient was nowhere on the chart the day or 2 days before. I would call that a surprise, right? And so instead of building a model that would reason about in the same way that a doctor might reason, we thought if we took a data set like this, that was the positive, these surprises, and trained it up, we'd build a model that would be reasoning at the frontier of human knowledge. It's figuring out the blind spots and the lookalikes, for example, and it's using machine learning to discover patterns of what things hide from human cognition from experts. Now, this picture is funny to me, but you always hear from physicians over the years I've been in AI and medicine for a number of years, I don't need your system. It's like, I know how to do diagnosis, or it's fine, it's a fun project but for a PhD thesis, but it's not the way we work in the hospital. In this case, the system is saying, upon discharge time of a patient, hey, do you want to look I think you might be surprised by this. Do you want to see what I'm thinking? And you can't imagine a doctor saying, don't show me how I might be surprised tomorrow. So there's a notion about how you build a system and what you aim it at in terms of cognition, right? The surprise model, for example, in this case. There's a phrase used that we're pursuing now called failure to rescue, which is a certain subset of deaths in hospitals happen where there's a missed treatable complication, and the patient begins to crash towards death with a multiple organ system cascade or failures. And we're trying to really figure out how to do that well, how to capture that from large data sets, working with the University of Washington Hospital data right now with a student, Dae Lee. Big upside there, by the way, if you think about 250,000 people per year quietly disappearing because of avoidable cognitive errors, largely cognitive errors, without any front page headlines or CNN articles about a shootout somewhere, or it's a city the size of Miami or Oakland going away every year quietly. So big upside here. The comment I would make to this group is that there's this opportunity to leverage richer cognitive models that come from the psychological literature and from psychology. And we've tried to adapt some in a paper with Shamsi Iqbal and others. We looked at driving simulators and various kinds of distraction, different kinds of tasks, and went to the psych literature. You can read about what we did to figure out, okay, what can we figure out about what's particularly dangerous to do in cars? And we've now carried this over to self-driving cars or semi-automated cars. But it really took us back to really, really great work by folks like George Sperling and Melvin Melchner, who basically did work on dual task scenarios. What are the trade-offs, and what's the attention operating characteristic curve? And how does this apply to multitasking and driving and all the things we do now? And what new studies might we do on top of the earlier work in the 70s and more recent work to understand this, how minds react to, for example, tasks and dual tasks, and these days triple tasks and sequences, even alluding to Wiccan's multiple resources theory, what our minds actually are. So this is just to say, this is background. It excites the AI and HCI researchers a great deal. So let's move on to coordination of initiative, because it's not just complementarity, it's how it's injected and when in a problem-solving setting. So if you think about it, we have human and machine intelligence, and we're going to figure out how they work together and how they can complement one another, and we can do studies of that form, drawing upon psychology and computer science and other fields. But then there's a design for how these systems work together. What's the mix of initiative? Is it a simple back and forth, like a dialogue system, or something more impressive and fluid? Let's take it to surgery for a minute, because this is a very, very graphical example that I like to use, or it's easy to see. And I'm on the advisory board at Johns Hopkins, not far from here, at CS. And you can imagine that Johns Hopkins would be would have a computer science department that looks at medical problems and medical opportunities, like surgery, which is a center of excellence or an area of excellence for Johns Hopkins. Now, what you see here is work by Carol Riley and Greg Hager and others from several years ago of using machine learning, in this case what's called an HMM model, hidden Markov models, to detect a predefined grammar of surgery. So if I had a camera automatically looking down at what a surgeon was doing, the system can figure out, oh, this is a positioning, this is reaching for a needle, this is a loosening, this is a dropping, this is a right transfer, a left transfer, a pull, and so on. And the idea is once this was automated and the system could figure out these predicates or verbs and adjectives of surgery, you could build demo systems. This is not real tissue. This is looks like more like something I want to eat for breakfast, some cookie dough here. But what you see here is a system that's just demonstrating how someday a tool could be built, a robotic surgical assistant that lets a human, manual mode, do some hard work, figuring out where like a suture needle might go, but then transfers over and says, I'll take over and I'll do the tightening and so on. And you can imagine this speeding up, and there's some newer work that goes even faster now But the idea there's a mix of initiatives with recognition on both sides of what's going on. And in this case, you can imagine this is a huge design space, but some basic signaling happens here with auto and manual and the back and forth. But that's this back and forth, and even the way you talk to your Alexa device, for example, as simplistic as that is still early days for initiative, mix of initiative. And what I've been very excited about, and my colleagues, is the idea of grounding of an understanding with a collaborator, whether it be human or machine, and then leveraging that grounding or mutual understanding for fluid collaboration. And the graphic here I like to use looks like this. Here's the problem or the challenge at someone's focus of attention. A computer system says, you know what? I see the human being looking at that. There's engagement going on. I can decompose that problem into alpha and beta. And you know what? I can actually communicate that I'm doing this as a computer. And I can actually say to the collaborator, my human pal, that I'm going to solve beta, but I can't touch alpha. That's the human side. And imagine this happening in a very fast way and recursing, continuing over time, with signaling showing there's acceptance and understanding on both sides, this idea of grounding. Now, I have to say that one of my students years ago, Tim Peck, who was working with Herb Clark at Stanford, of work by Clark and Brennan and others, fame, that there was a really rich psychological literature and set of studies and efforts, Herb Clark, Duncan, Goffman, Goodwin, and Kendon. I'll put up a kind of a graphic that comes out of the Clark work that said, when people work together, when they have a conversation, when they get stuff done together, there's a layered approach to where there's a channel that's identified, voice or gaze or combinations. There's signals that are agreed upon that are understood on both sides. There's inference about intentions on both sides. And then there's the control of the perception and the dialogue, utterances, conversation. And we've worked to understand how to weave these ideas, which are just beautiful, and which we all rely upon daily without even thinking about the challenge is, to build systems that can do more fluid grounding and engagement. And we've done this within a project we call the Situated Interaction Project, led by Dan Bow, who's on our team. But here's the idea. Could we take the ideas from Clark and Brennan and Kendon and Goffman and others and think about the computational aspects of all of this? Can we do fine-grained coordination between people? Can we give systems a basic understanding of the physicality of situations, time and space that people are immersed in as part of the grounding? Can we give machines, I'm saying, basic social intelligence to know in a group, for example, that there's two people you're working with, not one? Can we make inferences dynamically about the attention and goals of people? Can we have a long-term memory? So when I come back to my system, hi, it's been a long time, what's been going on? Or, oh yes, I remember that from last time. And have grounded memory where you share salience about what you remember, and you know that an agent, of course, will remember something that happened 3 days ago. And then natural language and gestures and so on. So you can imagine someday, this picture here is always think it's a funny one. It's like, it's 32 years from now, and you're going out to whatever you do in 32 years from now with your wife or husband, partner, and you leave the kids home with the situated, interacted, the fluid, robotic overseer. You're just completely confident that it understands these things on the left, and it'll call you if there's a problem. Or you're in your kitchen and you're working on a recipe someday, and you have this ambient intelligence that understands, oh, no, pour it, but not that fast, slow down. And it's just with you at all times in a fluid way. You can imagine there's interesting challenges here of not understanding who and what and who's gazing at who, and the rich social dimensions of the problem. So what you see here is an early project we set out to do. We took cameras with disclosure in our reception area at our main building, Building 99 at Microsoft Research. What you see is a camera on the receptionist here, and watched for several weeks people's interactions with the receptionist. how did gaze work? How did dialogue work? How did people queue up? Who waited patiently? Who came to the foreground? And so on. And based on this, built an early system that Dan and I knew a different hairstyle that would actually could work and do have the basic competencies for like scheduling and providing services. And I'll show you a little bit of how that looks. Project.
That's great. That's great. On the Teacher Interaction project?
On your project, on your team.
That's fantastic.
Hi. My name is Laura, and today I'm here to help the receptionist with shuttle reservations. What's your name?
I'm Dan, and this is Eric.
Nice to meet you. Do you need a shuttle?
Yes.
Which building are you going to?
I forget, where are we going?
I think it's building 9.
You sure?
Yes.
So, you're going to 9, right?
Yes.
And this is for both of you, right?
Yes.
I'm making a shuttle reservation for building 9 for 2 people. In case you want to correct anything, say or press star over.
Okay.
Are you visiting someone?
Okay.
Yes.
So I think
I'll
everything
help
should be
you
all set.
register in just a moment.
Fabulous.
Okay.
I think we're set.
Okay.
Excuse me, sir.
Yes?
You will be on shuttle 53. It should be here any second.
All right, thank you.
Bye-bye.
Bye.
So you see in the background,
Hi.
Hi.
the system
name
is looking
is-
at even looking at the clothing type, formal. At Microsoft Corp, almost no one dresses that way, so he's obviously a visitor. And the system is making that inference, among other things it's doing here. So this work led to several projects. The one that I'll talk about for the next few minutes is called The Assistant. By my door, it's been running for a number of years now. And the idea was to take some of that work you saw earlier in attention and memory. We had these modules like cost of interruption, memorability, probability of forgetting various things, and built a system that sort of sucked in many of these modules from different projects. What I would forget, the cost of bothering me, the predictions about presence, message urgency, models of shared memory, and built a system that we've been experimenting with. And to give you a sense for the what it looks like walking up to it, I'm gonna go back again here, walking up to it here. That's my office down there. I'm having some control problems. Here we go. One more time. I want to give you a sense for how this looks, because this should be. Okay, one more time. Here we go. When you walk up to the system, here's what you see. We changed male and female. We don't want to be.
Hi Eric. No one has stopped by to see you since we last talked. And Outlook Mobile Manager is still down, so I'm not seeing messages from your email. Catch you later. Bye-bye.
So that's what people see, and it's again, we alternate between genders. Chad and Monica, actually we scanned these are actual people we scanned before they left Microsoft. It's kind of funny. They were happy to give us their personas, at least their facial features. And I'll show you, I'm going to show you a video in the wild now of an intern coming to see me who I didn't know, to just say hello, and she was a little bit nervous here, but just watch how the system works with her. We need more fluid interaction with my controls here. Here we go.
Hi.
Are you here looking for Eric?
Yep. Yes.
Eric is talking with someone.
I can
and
see
this might
that.
take a while.
Oh.
But I don't think he'd mind a brief interruption right now. Would you like to show him now? Okay. You could check back in 15 minutes or so, and we can see if he's available then.
Okay.
And another option, we could set up an appointment. Would you like me to check his calendar to see if he has any free time later today?
Yes.
All right. No, his calendar shows that he's fully booked today. I'm not sure, but I don't think he'll be attending the meeting on his calendar today at 1:30 p.m. I could pencil
That's
you
like
then.
now.
Would that work for you?
Sure.
Great. Would
Great.
you like me to write this on his calendar?
No.
Okay. Feel free to stop by at that time, but I'm not
Wow.
certain he'll be
This
here.
is amazing.
Yes, I'll see you later then. Bye.
Nice meeting you.
So things have evolved, and here's where things are now. If the video people can click on that video, because it should be starting by itself. Up, go back. I'm just going to click on the video itself. There we go. This is today at Microsoft Research, the ecosystem we have.
Huh? Do you need directions?
Yes,
Who or what are you looking for?
Eric Horvitz.
You said Eric Horvitz, right?
Yes,
Eric Horvitz's office is 3126. To get there, go to the end of this hallway. Turn left and continue on to the end of the corridor. Eric's office will be the last office on your right. By the way, I'll let Monica, his virtual admin, know that you're on your way.
thank you.
No problem.
Hi. I was expecting you. The robot told me you were coming. Are you here looking for Eric?
Yes,
Are you here for the 5 o'clock meeting with Eric?
no,
I'm sorry, I thought you were here for that meeting. Could you please swipe your badge? Eric is not here at the moment. Let me look at his calendar to see if I can tell where he is. His calendar says he should be at a meeting in his office now, so I'm actually not sure where he is. He will probably be back in around 15 minutes or so. Would you like to leave him a note, or maybe come back later?
we'll come back later.
Okay, you could try sending him an email message. I expect him to look at his email in around 10 minutes. Guess I'll see you later then. Bye bye.
Thank you.
So these systems have been pressed into service. They've been a number of papers based on analyses of these.
Hello.
Hi Eric.
Let me just move
Two
ahead
people
here.
stopped by to see you.
So I wanted to just mention now that what's going on in our systems is, as clunky as they are today, we're doing grounding at multiple levels. There's the idea of understanding confidences about what's being seen, what's being said, confidences and confusion about the conversational flow, and even the domain knowledge. And what I'm putting up here is not meant to be decoded by the audience. But what it is to me is it's showing measures of uncertainty or entropy at all these different levels. And this is what developers in our team and interns and grad students, we look at. And Tomas Pesha was with us a few years ago out of Bilge's team, Bilge at the University at Madison in Wisconsin. And the idea basically was, we said, let's convert this picture to control muscles to give human beings cues that would more naturally ground another human being with a machine. And I want you to, I'll play this little segment. Carefully watch the expressions all being driven programmatically by a system based on inferences in real time. So audio will come up automatically in a few minutes, but people by my door here, this is the Monica.
Hi there. Are you here looking for Zach?
Yes.
Are you here for the 2 o'clock meeting with Zach? Sorry, did you say you were here for the 2 o'clock meeting with Zach?
Yes.
Is one of you John?
Yes.
Sorry, I can't tell who is speaking when you stand so close together. Which one of you said they're John?
I did.
Right. Hi John, Zach is expecting you. Will you be joining the meeting? Sorry, will you be joining the meeting?
Yes.
Alright, I've let Zach know you'll be joining his meeting with John. I'm sorry. I think Zach is running a little bit late. I'm pretty sure he's on his way. Just to be safe, I'll send him a note to let him know that you're here. Feel free to have a seat while you wait for him. Guess I'll see you later then. Bye bye.
So what gives me a tingle up my spine is, even though it's early on, the idea that we take these important inferences about failures at different levels and uncertainties, and we're blasting them through the human channel, even though they're subtle cues right now. And that what this might mean for the future in terms of the fluid engagements we could have with machines of the future, where we're actually seeing, and we sort of, and I always say it's like, okay, well, do we really have the semantics down, or is it just artificial? In this case, when you see a knitted eyebrow and a squint, it's real. The system has, the semantics match. The system is not seeing very well. It needs to understand better. Please separate. Please stand further apart. I don't know where Eric is. I see the distribution, the agent thinks. It does the right expressions to show that. Anyway, we have a number of projects going on exploring these interesting ideas. And I want to just sort of end by saying that, before we get into Q&A, that it's kind of wide open territory right now where we're heading in this space. And I feel like we've just have our little pinky toe in the water. And I know there are social psychologists in the audience and human-robot interaction people that have taken different dimensions of this work much further. I did want to end by saying in this world that we're in, these issues are becoming not just laboratory inferences, but they're becoming safety critical concerns as these technologies move, sometimes maybe prematurely, into the open world. I drive a Tesla, and I understand, given my own accident on autopilot, that took out the rear suspension of my car and cost the insurance company $15,000 to repair and put me at risk. The concerns with not getting the human AI automation correctly, and the idea that there's even in the initial designs, which weren't done at a university, but they were pretty impressive nonetheless, of how a Tesla communicates, for example, when it's an autopilot, about its confidences, and in some settings, it's overconfidences, things it just doesn't know about. This is an actual picture I took one day on autopilot. I said, okay, I better take this thing out of autopilot. I'm sure that this was not a test situation in Fremont at the Tesla plant. So there are long-term challenges we've all seen over the years, and these are actually challenges with grounding, coordination of initiatives, grounding on state and attention, and these aren't even the most modern examples. There's some really, really deeply interesting challenges in failures in flight, for example, in communications and understandings between an autopilot and a human being. If you want to read a hair-raising story, read the China Airlines 006 story, where 747 went supersonic and almost hit the water before it was righted a few thousand feet off the water on its way between Taipei and Los Angeles, because of a different understanding between what the autopilot thought and what a pilot thought as handoff was done. And then more classic problems where the humans being confused and not knowing state of a machine who can't communicate the state, like the Air France 447 flight coming from South America heading to Europe. So I want to stop here and say that I want to call back and reflect about, as we end here, what Licklider, J.C.R. Licklider said the goal was. And I think we will have this in our lives someday, even in our own lives, if not our children's lives or grandchildren's lives, of having computational colleagues whose competence in a deep and rich and fluid way supplements our own. But it's going to require lots of work and a much tighter coupling between human and machine. So I'll stop there. Thank you. And I guess there's a few minutes for questions, right? Okay. So I guess we go open mic and get to reflect together about anything you saw here, including my Tesla accident. I have other stories to tell also about in healthcare and so on, but I'm sure you have your stories too. Yeah. So we have microphones, I guess, or? There's actually a runner here who's running really fast. That's why they call him a runner.
Hello? Okay. So as someone who is teaching students in different countries with different languages, I was very interested in the automatic translation. And is that available to at a cost that's affordable for a small institution or an individual?
These technologies are available for free.
Okay, and
For Microsoft and Google and other places. I mean, there's a nice competitive terrain right now, but Skype Translate is free. There's also an application that people find mind-boggling. You can download the Microsoft Translator on your iPhone, for example, and it's like being on Star Trek in 1968, but it actually works. I mean, it's really literally like you talk into your cell phone, and it'll translate in language, to voice to voice to another human being.
so I don't need
many common languages.
so I don't need a Pixel phone. I can do it with iPhone and Microsoft.
I think it runs on many different phones. Yeah.
Okay, thanks.
Hello. Thank you. That was a really fascinating talk. I was particularly interested in the theme you talked about of people's blind spots, helping people to mitigate and kind of rescuing people from their cognitive blind spots. And I was curious about your thoughts on, do you see a role of technology not only in kind of jumping in and rescuing people from fixed blind spots, but actually improving people's insight and mitigating and ultimately trying to remove those blind spots themselves, as well as just rescuing people from them?
Yeah, there's a whole. We should not be overly focused ever on the fact that this is a real-time system that has to do real-time work. It can actually be aimed at insight building, visualization, education, even documentation. So you can imagine if I can go through 16 years of a hospital's records. So in healthcare, there's something called an M&M, morbidity and mortality report for patients that pass away. Many of you know about these reports, and there's a big conference of what happened. How could we possibly have had this happen at our hospital? And those are learnings. You'd hope they're not just for the now and for like a single report, but you'd hope that there would be learnings over time as to what practices might change, what we might learn, what new insights we might build. When I talk about decision-making in automation, I often talk about this idea of the data to predictions to actions, but I always say that a big part of that needs to be visualization and insight building. So I agree with the intent of your question. I think it's really important we think about the bigger picture and also about concept attainment and learning, educational applications.
So
Yeah.
I have a question. Back over on your right side,
Okay.
in the back, with all the West Point students.
Yeah, I see.
Okay.
Getting it.
So, sorry. So I had a
See
question
my,
about...
my red dot of the gaze, like the
Yeah.
avatar. Actually, yeah.
So I had a question. I work at a testing company that uses AI to score essays and things of that sort. And one of the challenges we've had is that it's very important to be able to explain what the AI is doing. And you had one slide up there where you were showing that, what do the humans need to know about what's going on behind the scenes. And in my experience, if you really want AI to collaborate, it needs to do something that a human isn't doing. Otherwise, you're just mimicking the human. So to get to that point where it's really doing better, it needs to do something that humans may not understand. So I was wondering if you could maybe react to that idea
Yeah,
that
that's a good point.
if humans don't understand it, especially in like a high-stakes situation like medical or assessment or something like that, how do you really get them to work together?
Yeah, it's a great question. So let me first say that the grounding example in a dialogue, for that example, I thought there was good fidelity in what needed to be communicated per the flow of the conversation and the perception and the information sharing that was going on. So that was kind of a nice, probably application of human-like, as opposed to saying, oh, it's not doing as well as you could do. I should show that graph to somebody instead and train them how to use it. I think in that case it was pretty good. But in general, there's a very, very big pillar of concern right now and study in the AI people and society realm, in transparency, which is often unattainable in inferences, but we'll call it intelligibility and explanation. And what's interesting to me is that explanation of AI reasoning systems was an actual, core topic in the 1980s expert system era. If you remember that, the previous hype cycle in AI. But people did theses and PhD work and papers and lots of publication on how do you take this logical reasoning system, expert system, and change it into an explanation or teaching system that would actually share traces of the inferences with human beings. And back in those days, we were the kind of grad student revolutionaries at the time who were going up against our advisors from the logical world doing probabilistic inference in medicine, for example. And we also thought, we need to explain, because that was the tradition of the time, our inferences, and did lots of work in trying to explain the way probabilistic inference and decision theoretic inference was working with graphs and charts and so on. But today there's been a growth of deep interest in how do you explain the inferences of deep learning models? How do you explain the inferences of decision forests, which are opaque in some ways? And so there's interesting work going on transforming them to linear models that you can sort of read out weights of observations, for example, plus or minus against the diagnosis, for example, and new kinds of visualizations. And so it's going to be interesting to see where that goes, because people are going to want to understand automation, and beyond wanting, there's actually regulatory demands now. So the European GDPR, which is coming into effect soon, talks about privacy and data handling and so on, but also has a section, I've got the article number, that says end users who are affected by AI automated reasoning systems for significant decisions need to have access to, and I think the wording is something like this, a meaningful understanding of the logic of the processing. Now, you can imagine at companies now who sell lots of stuff to the Europeans, it's like, oh my gosh, is anything I'm doing, we have to explain it and explain meaningfully the logic behind what the inference is. So it's interesting discussion going on in the field now and in the academic community about how to do this well. Yes.
Hi, my name is Paris AJ. I'm graduating in May with my PhD in psychometrics from Morgan State University. And I had a question about measurement because that's my big thing.
Are you in Corvallis or are you up in Portland?
No, we are in Baltimore.
You said, you said Ohio.
Oh, no, Morgan State University.
Morgan State, gotcha.
Yes.
You said Oregon State. Okay.
No worries.
See you over here. Okay.
So given there are blind spots or biases inherent in human cognition, has there been any discussion about blind spots in how you code, given you're using data sets that may already be laced with cultural biases, systemic biases? How does that then translate to the logic that is written into the codes that then power the artificial intelligence?
You ask me all these great questions that are part of the current world of AI in the open world. So yeah, there's actually a whole conference now in a rising field. We refer to it as FAT Splat now. It was FAT ML, fairness, accountable and transparent machine learning, which was a workshop folks in MSR, our team helped to co-found. Now it's FAT Star, which means all AI. FAT Splat is the phrase that's being used. But there's a rise of people very interested and concerned with the prospect, and it's a really true and deep one, that the data sets that are available come from a society that has all sorts of explicit and implicit biases, deep ones, as we all know. I was talking to my wife, I think like women just got credit card, the ability to have credit cards in like the late 60s or 70s. They had to have their husbands sign off on credit cards like as early as the 60s and 70s. So we have deep biases, gender, skin color, demographics. There's been some great pieces of work that uncover not just the nuances of this, but also how hard it is to even have metrics and to do the right thing with the prospect that systems someday, if they come into place, let's say the big example we heard about 2 years ago was the Compass system. A commercial company has a system that was advising judges on recidivism and at the time of sentencing and bail decisions, would this person in front of me return to a court date if they were let go without bail? What was the probability they commit a violent crime in the meantime, and so on. What struck me about that case, even not knowing the details, was the following. Knowing how medical systems work when we take them and you train them on data in one place, like MedStar, even we did this here. We trained a system for readmissions, predict readmissions in 30 days with Washington Hospital Center data here in DC, and applied it to Union Memorial, and it didn't work very well. Well, there's different covariates and you have to really retrain a model and so on. Just hearing that the Compass system was being used as a black box at many cities was scary enough. Forget the biases, it just couldn't possibly be doing a good job. Even if it was doing better than judges, for that matter, it's still the prospect that these systems are easy to replicate, and therefore they'll amplify on large-scale biases in a systematic way. I'll just make a comment right now. At Microsoft Corp, we have what's called the Ether Committee, which stands loosely for AI and Ethics in Engineering and Research, with 7 working groups. And that effort has shown that it has teeth in guiding Microsoft policy. It reports up to the CEO, Satya Nadella, and to what's called the SLT of Microsoft. I should also say that Microsoft got together with 5 other companies, Apple, Facebook, Amazon, IBM, Google, DeepMind, to create what's called the Partnership on AI to benefit people in society, a nonprofit that's now directed with a balanced board with civil liberties organizations like ACLU and scientific societies and academics. And it's a place for sharing best practices. So Ether board at Microsoft will be sharing anything it comes up with as a best practice along explanation, bias, issues about safety critical behavior of systems and their testing, engineering practices with the Partnership on AI, and we hope other companies will as well. It's a long answer to a short question, but I think it requires it. It's a very important area. Yeah.
Hi, Art. Gary Olson from UC Irvine.
Hey, how are you?
Hi. Do you have any examples from your research of your investigations informing a psychology research agenda? That is, that there are things that psychologists need to work on harder as a result of what you're finding in your work?
My first reaction would be that there already are existing areas of social and cognitive psychology that are already close to or perfectly aligned with the needs and questions being asked by greater society, as well as the earlier technical issues. But sometimes you need to there needs to be more investment in the end game to do the adaptation. For example, this whole area we're hearing about now on persuasion and manipulation of minds, of beliefs by information, you can read literature on that, and it's part of the whole world of marketing and on the positive side, or propaganda on the negative side for many years. But what does it mean when it comes to exposure to a device with a sequence of information and a plan for you that's personalized? What are the prospects there, and how would that work? We did a study a few years ago with crowdsourcing, just wanted to understand how showing people different search results, this was with Ryan White, different search results about medical efficacy of different procedures and medications would affect their beliefs. So it was a paper about how hitting people with a sequence affected their probability assessments on does this work or not, or what's the best treatment in this case. And the paper's online right now, but what's scary was we actually said, could I actually, and by the way, 4 years ago when we did this work, we said, let's do this because someday it might be used, we didn't say this in the paper, for political purposes. And, we said, now let's take this data set, build a data set, and then show how we could optimize a plan for influencing belief. All psychological issues, but probably not studied directly in a psych lab. So we have to sort of get on that. The whole area of interruption and recovery. I love the work by Olga Zigarnik. Look, 1923 or whatever it was. It's fabulous. How do people come back when they get disrupted to a task emotionally and per the efficacies? And Mary Shawinski, as you know, Gary, and others on our team, Ed Cottrell, myself, in the 2000s and so early 2000s, we did lots of studying about how would a design help you get back to where you were. With Shamsi Iqbal, the work on, we discovered in 2007 or so, or 2006, that in those days, at Microsoft, and this is the publication as well on our website, people were being interrupted by a notification that they had email about 4 times an hour while they were working on another task. And it took them about 15 minutes to get back to what they were doing each time. So you add it all up, you don't have a very productive day. And even worse, in another paper, I say even worse, or just another factoid, when you turned off somebody's alerting system, who had used one, with the toast that comes up, as they call it, they did more self-interruptions to check their email to see what was going on, because they felt like nervous. They didn't know what was going on now. The whole study, and there's been several papers since then about self-interruption. So I guess we don't even understand the influences. I just told Shamsi recently that I want to take the exact same tools we used in 2006 that were looking at email disruptions and roll them out to a similar cohort at Microsoft Corp widely, and see what's happened today with Facebook and Twitter and social media and other things going on, just to get a sense for maybe the change of population too, but the sense for what's happening now with these multitasking platforms we call the world of computing, which we're all immersed in all the time. So there's lots to do. I can imagine many other things I'd say. Social psychology, there's, how do people react to systems? We hear this, I'll mention one more issue. We hear this statement about uncanny valley. Don't make your system look too much like a person, or people get really weirded out and they look for precision, and we call it the uncanny valley. Well, guess what? That whole concept, from my understanding, came from one paper from Japan. One study, one reflection, one paper. Everybody talks about it because it makes so much sense. But we don't understand it very well, how people work with machines of various kinds and their presence and their comfort levels and what it means to collaborate with an intelligence that might act and look like a human in some cases, but not really have any feeling behind the pixels. Lots to do.
Ladies and gentlemen, it is now 10 o'clock. We can take one more question.
Can you hear me?
Yeah. Yes.
Hi, Eric. Fascinating presentation. Thank you. I'm running a startup in San Francisco. Just full disclosure. One of my questions that I get sometimes in terms of AI is, for example, we've heard Elon Musk and Stephen Hawking talking about the risks of AI. And one question I have for you within Microsoft. Do you think about the question and how do you respond to that, which is like, if you can build it, that's fine, but should you? Have you encountered a type of projects that, that question came up, and how did you answer it?
So there's the idea of, should you pursue research to learn more about the computational foundations of intelligence, or a psychological issue with relationships between people and machine? So the idea of research and studying research questions, and typically I'm always a big fan of not saying, no, you can't do that study. That said, places like Microsoft, just like universities, we have an ethics advisory panel and an IRB process for looking at data, for doing sensitive studies. That's reviewed by a full, institutional review board. And people are called to task on the ethics of what it is they're doing on the research side. On the fielding side, it's an interesting question. So one of the committees, one of the working groups on the Ether committee at Microsoft is called Sensitive Uses of AI. And it's very, very carefully, I actually sit on that committee, so I know how it's, I've been part of the discussions, but it's been very carefully looking at questions coming up along the lines of, should Microsoft consulting teams build this thing for this end user? And all I can say is that that committee has teeth. So I'll end there.